So, welcome to my YouTube channel, and today I'm going to discuss something to do with matrix, why we need these matrix in engineering, and also how to apply the matrix in engineering, and also that is now for in terms to engineering, matrices is a very important concept that is mostly applied in, or used in engineering mathematics. And as far as engineering is concerned, the concept of matrix refers to a rectangular array of numbers, symbols, or expressions arranged in rows and columns. And these mathematical structures are used to represent and manipulate data. They used to represent and manipulate data and in various engineering applications. So the main aim of this area, that is the matrix in engineering, it helps in simplifying solid information or solid data, and thereby we end up having a simplified structure which can be solved. And therefore, there are several things that when it comes to matrix that we need to have a concrete understanding. And one of those things is the structure of the matrix. So a matrix is typically denoted by capital letters. So we use capital letters to represent a matrix. So and inside that matrix, we have the column and the rows, and we have the column and the rows. So the numbers are arranged in columns and in rows. So for example, it can be a 2 by 3 matrix, or 2 by 2 matrix, or 3 by 3 matrix, depending on what is provided, depending on the information provided. Then there are types of matrix. We can talk of a square matrix, and a square matrix is a matrix whereby the matrix with the same number of rows and columns. So a square matrix is a matrix that has the same number of rows and same number of columns. So they are the same. So you find that if there are 3 rows, for it to be a square matrix, if you have 3 rows, then it means you must again have 3 columns. And for example, is when we talk of 2 by 2 matrix or 3 by 3 matrix. Then we have a row matrix. A row matrix is a matrix with only a single row. It's only a matrix that has a single row. And we can say for an example, it is 1 by an nth number of columns. Then we have a column matrix. This is a matrix with a single column, a matrix with only a single column. And for example, we can talk of m number of rows multiplied by 1 single column. So it is an m by 1. Then we have the 0 matrix, and a matrix in which all elements are 0. So you find that this is a kind of a matrix where all the elements are 0. Then we have an identity matrix. An identity matrix is a square matrix with one of its diagonals, one on the diagonal and 0 elsewhere. So it's a matrix whereby we have the leading diagonal being represented by a value of 1, and all the other elements are represented by 0. Then the other thing that we need to understand when it comes to matrix is the operation of the matrix. And in this case, you can say that matrices can be added, they can be subtracted, and multiplied following specific rules. So we have specific guidelines for what we call the set standards, and in other words, they are referred to as the specific rules, whereby operations such as addition, subtraction, and multiplication are performed based on those specific set rules. Now, these operations are essential in solving systems of equations, transforming and coordinates. There's also transforming coordinates and also effective for data analyzing. Then the other thing is where are these matrices used, or where do we find the applicability of these matrices? So in a general, matrices are used to solve linear systems. Though when you talk of a linear system, it's a system that will automatically generate either linear equations to express a certain crucial information. And when you talk of a linear equation, the equation can either be two unknown equation, two unknown variable equations, or three unknown variable equations. And these are more in electrical engineering, whereby you find them in circuit analysis, and simply by the use of Kirchhoff's laws, you can simply get equations, and those equations can be solved by use of matrix. And when it comes to matrix, you can either use the solve by inversion, you inverse the matrix, and also they are also common in structural engineering. Then in engineering again, transformation, we can use matrix for transformation, and this is computer aided graphics and robotics. Matrices facilitate transformation of geometrical shapes. So those geometrical shapes can be solved and transformed using matrix. Then the other crucial element when it comes to matrix is the application. We have application in control, that is the control theory. Matrices are employed in state space representation, model dynamic systems, and design control strategies. So we have other specific applications, and when it comes to again these specific applications, we can simply say that matrices are used for data representation, and we can simply say that matrices provide a systematic way to represent complex sets such as coefficients in linear equations and state space or transformation of graphics. Then we have linear algebra application. Many engineering problems can be modeled using linear algebra, where matrices are used to represent systems of linear equation. And this is very crucial for solving problems in structural analysis, electrical circuit analysis, and also in mechanical when you're interacting with forces, and also in mechatronics. And again, it comes to the interaction of robotics. Then I had talked about transformation. This is whereby you, in the field of computer graphics and robotics, matrices are used to perform transformation, e.g., you can perform rotation, you can perform scaling, you can also perform translating. You can translate an object, you can rotate an object, you can scale an object, and also you can define through this transformation. You can define the trajectory of moving objects or moving particles, and they allow for efficient manipulation and coordination in 2D and 3D spaces. This is whereby you can be able to view your transformation either by 2D or 3D, and this is simply done by use of matrix. Then in control engineering, matrices are essential for state space representation, enabling the modeling and analysis of dynamic system. They help in designing controllers and observers. Then there is signal processing. Matrices are used in digital signal processing for operations such as filtering, image processing, and in this signal processing, we incorporate both matrix and Fourier transforms to represent them in a matrix form to facilitate efficient calculations. Then there is the finite element analysis, and this is more so applicable in mechanical and civil engineering. Matrices are employed or they are applied for finite element analysis to analyze complex structures. And in so doing, you find that these complex structures, for specifically for mechanical and civil engineering, they are more so simplified and made easier to be solved. And we can talk of the stiffness and mass matrix are key components in determining how structures respond to load. Then we have the optimization problems. Many engineering applications involve optimization where matrix helps to formulate and solve problems related to resource allocation and system design and performance improvement. This is in cases of where you have a designing problem. You want to design something using a software, and through the help of matrix, you can be able to formulate and solve that problem relating to how you will be allocating your resources, how your system will be designed, and also the performance improvement of the same system can be done by the use of matrix. Then we have network analysis. When it comes to network analysis, this is specifically applied in electrical engineering, whereby you find matrices represent network through techniques such as nodal analysis and mesh analysis. They help in analyzing the behavior of circuit and systems. So, as far as matrices are concerned, they are very useful in engineering, and not only understanding the mathematical concept of it, but also understanding how they can be used in designing, they can be used in modeling, they can be used in again designing and crafting. So you can use matrix to design from the scratch until you come up with an entire structure. And if you are a fan in robotics, you require coordinate matrix to define the trajectory of your robot, to define the arrival coordinate of your robot, and also to be able to know the trajectory of that robot. Then specific in electrical now, matrix are applied, I've said one, in circuit analysis, and that is by the use of, whenever you find nodal or mesh analysis, it is very crucial that you think of the matrix. So matrix in this case helps to formulate and solve nodal and mesh equations in circuit system. The admittance matrix, that is the Y matrix, and the impedance matrix, the Z matrix, represent relationship between voltage and currents of complex circuit. Then again, in electrical engineering, there is the control system part, and this is specifically when it comes to state space representation. Systems are modeled using state space equation represented in a matrix form, and this allows for analysis and design of control system using techniques like pole placement and observers design. And again, we have the signal processing. When it comes to digital filtering, matrices are used in the design and implementation of a digital filter. For example, the convolution operation can be represented using matrix multiplication, facilitating, and this facilitates efficient signal processing. Then again, in power system analysis, when it comes to load flow analysis, matrices are employed in load flow studies to analyze power distribution network. The bus admittance matrix, that is the Y bus, helps to determine voltage levels and power flow in the systems. And again, in electrical engineering, matrices are used in electromagnetic field, that is electromagnetic field theory. And when it comes to electromagnetic field theory, we are talking of finite element method, whereby matrices are used in solving finite element method problems. The formulation involves creating matrices that represent the relationship between electric field and material properties. Then we have again in electrical, we have the communication system networks, and this is whereby you have the multiple input, multiple output systems. In another name, they are referred to as the MIMO systems. And here, matrices are used to model the relationship between transmitted and received signal, and this enables efficient data transmission and the spatial diversity of the same signal and again of the same system. Then in engineering, we have the imaging, processing, and transformation, and this is applicable in the case of electrical. So matrices are applied in image processing tasks such as image filtering and enhancement and comprehension. So operations like transformation and convolutions are employed using matrix algebra. And then there is the issue of, again in electrical, the network theory, whereby matrix represents electrical network through adjacency, and in indecence matrix aided in the analysis of network connectivity and the flow. So have you ever asked yourself, where do we require matrices in mechatronics? In mechatronics field, do we require matrix? In mechatronics, do we require the application of matrix? In mechatronics, do we require the application of matrix? Yes, and these are the areas of application. They play a very vital role in analysis, modeling, and control of integrated mechanical and electrical systems. So when you talk of a mechanical system, so the mechatronic system, it is a system that integrates both electrical and the mechanical systems. Now, electrical is to provide the power, the driving power, and the mechanical is to perform the actual task. So when it comes to mechatronics, matrices are applied in system modeling. And when you talk of system modeling, you simply refer to as the state space representation. So mechatronic systems are often modeled using state space equations, which involves matrix to represent the dynamics of the system. And this allows the analysis of complex interactions between mechanical, electrical, and control components. Then we have the kinematics and dynamics. This is the transformation of matrix now. In robotics systems, transformation of matrix are used to describe the position and orientation of the robotic arms. These matrices facilitate the conversion between coordinate frames and essential for motion planning and the control. Then again, still on the kinematics and the dynamics, we have the Jacobian matrix, and the Jacobian matrix relates to the joint velocity to end effect velocity in robotics arms, crucial for trajectory planning and control. Then again, we have the control system, and in mechatronics, when you talk of control systems, simply refer to as the control algorithms. Matrices are used in in the design and control algorithms such as the PID controllers and state feedback controllers, and they help in formulating the system's response to input and disturbance. And again, still on control systems for mechatronics, we have the observer's design, and in state space estimation, matrices are utilized to design the observers that estimate the internal state of a system based on output measurements. Then again, when you talk of mechatronics, there's the issue of signal processing. And when you talk of signal processing, you're simply referring to the data filtering. So matrices are used in filtering techniques for sensors data, enhancing the accuracy and measurements in mechatronic systems. Techniques like the Kalman filtering can be expressed in matrix form. Then there is the simulation and analysis. And again, we talk of finite element analysis. In mechanical designs, matrices are employed to analyze the stress and deformation in structures. So the stiffness and mass matrices are employed for understanding of crucial behavior and crucial behaviors of structural systems and load. Then we have system identification. And this is specifically for mechatronics. So you have parameter estimation. Matrices are used. That is the parameter estimation. Matrices are used for matrices are used in system identification techniques to establish model parameters and model experiment and model parameters from experimental data, enabling, and this is for enabling of accurate models for control and analysis. And then how do we apply this matrix in building and construction field? Building and construction field. Are matrix important for building and for the construction field as part of the engineering? So when it comes to building and constructions, matrices are very important, and they are used for analyzing various purposes, particularly in structural analysis, design, and project management. And one is for building and construction, we have the structural analysis. And when you talk of the structural analysis, in simple terms, you're referring to as the finite element analysis. The stiffness matrix represents the relationship between the nodal displacement and force. So these matrices are crucial for determining how structures respond to load. Then you have the mass matrix. The mass matrix is used to analyze dynamic responses, helping engineers to understand how structures behave under dynamic loading conditions such as earthquakes and wind. Wow, that is very, very crucial. Wow. So again, we have the load distribution matrices. That is load distribution matrices are used to represent load distribution across structural elements. This aid in analysis, analyzing how loads are transferred through beams, columns, and slabs. Wonderful. Wonderful. Then we have the geometric transformation. The transformation matrices in computer-aided design, what we refer to as the CAD, and the architectural modeling. Transformation matrix helps in manipulating geometric shapes, allowing for the creation of complex design and structures. Hey, these are wonderful. Then you have the project management, resource allocation. Matrix can be used in project management to represent and optimize resource allocation across various tasks and projects, ensuring efficient use of materials and labor. So when it comes to resource allocation, that is for project management. It simply means that you have to design to model a system which is now able to help you distribute the resources available. For example, you're in a building site or you are in a construction site, you need to know at what point you need to spend what accuracy of materials. And this will help in the planning and also when it comes to running the project. Then again, under project management, that is under construction and building, matrix are used for scheduling. You do your schedule. So matrix helps to schedule tasks by representing dependencies and timelines, allowing for better planning and execution of construction projects. Strong points. Building information modeling. We have the data representation. In BMI, that is the building information modeling, matrices are used to manage and manipulate large set of data relating to building of components, structures, and their interrelationship, facilitating collaboration among stakeholders. Then there's the environmental analysis. Wonderful environmental analysis and matrix method in environmental engineering. When assessing environmental impacts, matrices can be used to represent relationship between various environmental factors and construction activities, aiding in decision making. So you can simply say that a matrix is an essential tool in building and construction, facilitating structural analysis, project management, design process, and the ability to organize and manipulate complex data makes them invaluable for engineers and architects in creating safe and efficient, sustainable structures. Imagine this is a house. Imagine you're in a house whereby on one side of that house or in one section of that house, there is insufficient use of cement or application of the joining material, that is the mortar, was not effectively mixed or it wasn't effectively, let me use the word cooked. It was not effectively cooked. That means there was no sufficient water during mixing or there was not sufficient cement. So there's a lot of sand in it. So that will make that structure or the structural building to be weak on that one side. So by use of this matrix, you are able now to design and allocate your resources well without overlooking on one section and also overdoing in another section. So what about in mechanical engineering? To be specific, in mechanical engineering, where do we apply this matrix? So in mechanical engineering and electrical engineering and also mechatronics engineering, the application is more the same. So I'll focus on the following. So when it comes to mechanical engineering, you have the structural analysis, the stiffness and the flexibility matrices. In finite element system, our analysis, stiffness matrix represent the relationship between the nodal displacement and force. So flexibility matrix are the inverse relating force to displacement. Both are critical for analyzing structures under various loading conditions. Wonderful. Then we have the dynamics and kinematics, and as I had explained earlier, when it comes to mass matrix and the Jacobian matrix. Jacobian matrix applicable to robotic systems. Then we have the other application is on the control systems, and that is the state space representation. So mechanical systems are modeled using state specifications which involve matrix representing the dynamics of the system. This is important for designing and control that regulates mechanical processes. Then, where now it touches mechanical specifically, we have the thermal analysis. In thermal analysis, matrices are used to represent heat transfer, coefficients, and temperature distribution in complex system. And these aid the design of mechanical thermal management systems. So if you want to have a good thermal or an efficient thermal systems, kindly do a consideration matrix. Then we have fluid mechanics, again in mechanical. So fluid mechanics, that is the flow matrix in computing fluid dynamics. Matrices are used to represent the flow characteristics and interaction within a fluid system, and this facilitates the analysis of fluid behavior around mechanical components. Then we have optimization. So matrix method for optimization. Matrix can be employed in optimization algorithms to solve problems relating to design and performance of mechanical systems, such as minimizing weight while maximizing the strength. Then we have application in mechanical touching on the CAD or computer-aided design, and this is specifically geometric transformations. In CAD transformation, matrices are used to manipulate geometric shapes, enabling engineers to create and modify complex designs effectively. Wonderful. So we find that in mechanical, matrices are integral. They are part of it. There must be application of matrix when you're designing a mechanical systems, and providing essential tools for structural analysis, dynamics, control systems, thermal analysis, and design optimization. They are versatile in handling complex data and relationship that makes them invaluable for engineers in developing efficient and effective mechanical systems. Wonderful. What about in what do you call this field? In telecommunication field, do you require matrix in telecommunication? Kindly rush to the comment section and tell me whether we do require matrix in telecommunication field, and if we require them, where do we require to use matrix in telecommunication? I'm waiting for your response. Kindly let me understand where you require matrix in telecommunication. Why do you require the matrix in telecommunication? And keep in mind that telecommunication is a branch of electrical engineering or a specialization of electrical and electronics engineering. But when it comes to telecommunication, the application of matrix is very crucial. And this touches things to do with signal processing, network analysis, and system design. All right. Now, when it comes to signal processing, we have the transformation of matrix. Matrices are used in signal transformation, such as the Fourier transforms and the wavelet transform, to analyze signals in different domains, that is in time domain and the frequency domain. And this helps in filtering, compressing, and feature extractions. So by the use of matrix, you are able to compress, to filter, and also to analyze a signal effectively. And again, this signal can be analyzed in the following domains. That is the time domain or the frequency domain. Still on signal processing, we have covariance matrix. In state signal processing, covariance matrix represent the relationship between different signals, aiding in noise reduction and signal estimations. Wonderful. Then the other application when it comes to telecommunication is touching on the network theory. That is the adjacency matrix. In matrix topology, adjacent matrix represent the connection between nodes in telecommunication networks. They are used to analyze network structures and connectivity. Then there is the incidence matrix. These are matrices that are used to represent relationships between the edges and nodes in a graph, useful for analyzing network flows and capacities. Wonderful. Then we have the channel modeling for telecommunication, the MIMO system, that is multiple input, multiple output systems. Matrices are used to model the relationship between multiple transmitters and receivers, and this helps in enhancing data throughout and data output throughout, and also the data becomes more reliable. So you can rely on that data, it becomes more reliable. Then we have the transfer matrices. Transfer matrices are a relationship, describe the relationship between the input and the output signal in a communication channel, essential for understanding systems behavior. Then, this is very important, matrices are used in error detection and correction. The parity check matrices used in coding theory. This matrix helps in error detection and correction by creating codes that can identify and correct errors in transmitted data. Then we have the generator matrix. These are matrices that used to generate error correcting codes, ensuring data integrity during transmission. Then again, matrices are applied or they find their use when it comes to modulation and demodulation. And matrix representation of modulation schemes. Various modulation techniques can be represented using matrix, facilitating the analysis and the design of modulation and demodulation processes. Then there is the optimization. When it comes to optimization, it simply refers to resource allocation. Matrices can be used in optimization algorithms for resource allocation in telecommunications network, ensuring efficient use of the bandwidth and the power. Then they are used in machine learning, specifically for data representation. In telecommunication, matrices are used to represent large data sets for machine learning applications such as predictive maintenance and network optimization. So matrix is a very important concept, very key, very vital. So never assume it. So make sure you have a solid understanding. And there is another area of application of matrix, and that is the aerial space. The aerial space. The talk of the aerial space simply means it is the study of the atmosphere, that is the space atmosphere. And when it comes to the aerial space, we have its application. It defines its application in these specific areas. One is signal processing, In avionics, matrices are used for data fusion techniques that combines both multiple sensors, improving the accuracy of navigation and control systems. Then they are used in design optimization. They are utilized in the optimization algorithms to improve the design of aerospace structures and systems, balancing performance, weight, and the cost. Then there is navigation and guidance. Transformational matrices are used to convert between coordinate systems, which is essential for navigation and guidance systems in aerospace applications. Then they are used in aerodynamics and matrix method in computational fluid dynamics are used in solving the Navier-Stokes equations, which describes fluid flow around aircraft and spacecraft, aiding in aerodynamic design and analysis. So do you require matrix in finance? Do you require matrix in finance? Do you require matrix in finance? So tell me at the comment section whether you require matrix in finance, and if we require it, in which specific areas do we require matrix in finance. We can talk of finance and banking system, whether we require matrix in finance and banking systems, and where specifically do you require matrix in managing your money, and maybe in managing your bank account or managing your business. And in finance and banking, matrices are utilized for various applications, and these include risk management and analysis. We have portfolio optimization and financial modeling. So when it comes to risk management and analysis, value at risk is something we call value at risk, and matrices can be employed to calculate the value at risk by analyzing potential losses in various portfolio under normal market conditions over a set time period. Then we have the stress testing. Matrices are used to simulate different economic scenarios and assess their impact on financial portfolios. Then we have portfolio management systems. And when it comes to portfolio management systems, we use covariance matrix. And these matrices represent the variances and covariance of asset returns, helping investors understand the risk associated with a portfolio and optimize asset allocation. Then we have the mean variance optimization. Matrices are used in the Markworth, that is the Markowitz portfolio theory, to find the optimal assets in weights that minimize the risk for a given return. Then when it comes to financial modeling, we have the cash flow models, and the matrix can represent cash flow from multiple sources, allowing for complex financial modeling and analysis of investments and projects. Then there is the discounted cash flow analysis. Matrix helps in calculating the present value of future cash flow, and this is essential for valuation processes. Then we have the we have the credit risk assessment, and under this we have scoring models. We have the credit scoring models. Matrix are used in statistical models to evaluate the credit worthiness of borrowers, incorporating various factors that influence credit risk. Then we have the time series analysis. And when it comes to time series analysis, we have an element or an area, specific area of application, that is the vector auto regression, the vector auto regression. And this statistical model uses matrix to analyze the relationship between multiple time series, allowing for forecasting and it allows for forecasting and understanding economic indicators. Then we have the market analysis, and the draw of the market analysis is simply referred to as the market analysis, where we have a specific application, that is the correlation matrix. This matrix allows for correlation coefficients between different financial instruments, helping analysts understand the relationship and dependency in the markets. Then we have the algorithm trading. So matrix operation in algorithms. And when it comes to qualitative finance, matrices are used in algorithms for trading strategies, including back testing and optimization of trading models. So in the field of finance, where the application is quite big, quite important. So the application of matrix is much important. And as per what we've discussed, or as per what you learned so far, it simply means that when it comes to engineering, specific electrical, mechanical, mechatronics, civil, and biomedical engineering, matrix are very important. And maybe in let's give an highlight when it comes to the medical field. Medical field. Where do we require matrix in medical field? Do we require matrix in the medical field? So give your comments in the comment section. Give your comment in the comment section whether we require matrix in the medical field. Yes, we require matrix in the medical field. And when it comes to the medical field, matrix are extensively used across various applications, and that include medical imaging, data analysis, and bioinformatics. And in medical imaging, we have the image representation. Medical images such as the MRI, CT scans are represented by matrices, where each element corresponds to a pixel value, and this allows for image processing techniques such as filtering, enhancement, and segmentation. Then we have the transformative matrices used to manipulate image, rotation, scaling for better visualization and analysis. And this transformation of matrix is very key. It's also very key when it comes to mechatronics design and the mechanical designs. It is also very key when it comes to designs in electrical engineering and telecommunication field. So again, we have the signal processing. In a medical field, electrocardiograms, that is the ECG analysis, electrocardiograms, ECG analysis, matrix are used to analyze the ECG signals, helping in the detection of arrhythmias and other heart conditions through techniques like wavelet transformations. And we find that this wavelet transformation is also required in telecommunication engineering. So when it comes to medical engineering, specifically to diagnose heart conditions, you require the use of matrix. So if you are a medic, matrix is very important in that field. If you are aspiring to be a medic, matrix is again very important in that field. Then we have under signal processing, we have the filter design. In signal processing, matrix helps design filters to remove noise from medical signals, enhancing the quality of diagnostic data. Then we have data analysis in the medical field, and that is, when we talk of data analysis, we simply refer to as the statistical analysis. And the matrix are used to organize and analyze large data sets in clinical trials, helping researchers assess the efficacy of treatments and interventions. Then still under data analysis, you have the multivariate analysis. The multivariate analysis, so the techniques like principal component analysis utilizes matrix to reduce the dimensionality and identity patterns. Then we have genomics and bioinformatics. Genomics and bioinformatics. And then there's the gene expression data. Matrices are used to represent gene expression levels across different samples, facilitating analysis of genetic variation with the association to diseases. So matrix is used to represent your gene sample, and in comparison with other, that is in comparison with the genetic formation of a certain bacteria that is known for causing a certain medical condition. So that comparison is done, and the diagnostic becomes valid. Once your gene matches with that of the causing agent, then the medic will tell you you have this condition. Yes. Then we have the phylogenetic trees. I don't know whether that is the mentioning. Phylogenetic trees. Matrix can represent relationship between different species or genes, aiding in evolution studies and comparative genomics. Then we have machine learning. So in the medical field, matrix are applied in preventive modeling. In health care, matrix are used in machine learning algorithms to prevent patients' outcomes based on historical data, improving diagnostic accuracy and treatment plans. Then again, in the machine learning for medical field, we have the neural networks. Matrix are fundamental in the architecture of neural networks, where the weights and inputs are represented in matrix form, enabling complex pattern recognition. Then we have another application in the medical field, that is clinical decision support system, matrix-based algorithms. These are systems that uses matrix to analyze patients' data and provide recommendation for the diagnosis and treatment based on clinical guidelines. So I find that this is a software that has been developed that is able to analyze a patient's conditions and signs and symptoms, and it's able to combine everything and give a reliable diagnostic. And also in cases where the patient is found to be with a certain underlying condition, then it is able to predict the medication. Then you have robotics and surgery. Robotic surgery. The robotic surgery uses matrix in the control algorithms of robotic surgical systems, and this allows for precise movements and coordination during the procedure. So, as you've seen, that matrix are very, very vital. They are very important in almost all fields, in almost all our careers, and you find they are taught in almost all the areas, in all the field of specialization. There must be some bit of matrix. So understanding how they work is very, very important. It will help you. It will help you to be well informed. So find out if I haven't discussed your area of study, try and find out if matrix are applied. Try to find out whether matrix are applied and let me know in the comment section. Please drop your thinking on the comment sections whether matrix are applied in your area of specialization, whether you require matrix in your area of specialization. Yes, let me know in the comment section. So share, subscribe, like, comment, and again tell a friend to tell a friend. Thank you. Thank you for your audience. Please share, subscribe. Thank you. Enjoy yourself. Enjoy yourself. And now this brings us to the end of our live streaming. Thank you very much. And as you can see, my T-shirt. I am a registered professional with the Institute of Engineers, Technologies, and Technician. That is IEK. This is our log. This is the log we use. So align yourself with a professional body that best suits your profession. Don't be left out. It is very important. It is very, very important. So thank you. Thank you.